Today's lesson is on inductive reasoning, conjecture, and counterexamples. Before we start with that, let's talk about seeing patterns. So, what comes next in this sequence? There's a shape, then the next shape, and the next one, and the next one, and the next one. And so to find out what comes next, we have to determine the pattern. So hopefully I'll give you a second to look at this. Hopefully you have seen a pattern. And what that pattern is that this shape has 3 sides. This one has 4, this one has 5, then 6, then 7. So the pattern is that each shape that comes next has one more side than the previous. So 8 sides. So the shape would look like this. And so to answer the question, what comes next in the sequence, the answer is this 8-sided shape, which we'll learn later is called an octagon. But hopefully you were able to see that pattern of 3, 4, 5, 6, 7 leading to 8. And if you did, then you just used what we called inductive reasoning. What is inductive reasoning? Inductive reasoning is reasoning that is based on patterns that you observe, or patterns that you see. When you see those patterns and then use it to determine what comes next, that's called inductive reasoning. If you observe a pattern in a sequence, you can use the inductive reasoning to tell what the next term in the sequence will be. So let's see if we can find a pattern in each of the sequences below. 3, then 6, then 12, then 24. Now hopefully, if you look at this for a while, you can see that each term is twice as big, or I multiply each term times 2 to get the next term. 3 times 2 is 6, times 2 is 12, times 2 is 24. So the next 2 terms would be the 24 times 2 to be 48, and then 48 times 2 to be 96. What if I have some shapes like that? Well, hopefully you see that the first circle is cut with 1 line, the next one by 2, the next one by 3. So each circle has one more segment through the center to form equal parts. The next 2 would have 4 lines and then 5 line segments to cut the circle. These are all just examples of inductive reasoning. Now, an easy way to remember this is that inductive reasoning begins with an I. So to remember it, what I teach my class to say is, I see a pattern. This will help you remember inductive reasoning versus a different kind of reasoning called deductive, which we'll learn about later. So, I see a pattern. Inductive begins with I. Now let's talk about another word, conjecture. A conclusion that you reach using inductive reasoning is called a conjecture. So, let's make a conjecture about the next number in this series. 2, 4, 6, 8, 10, and so forth. Well, using inductive reasoning, hopefully you can see that each number in the series is just 2 more than the previous number. We're just counting by 2's. So 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, and that pattern holds for all of them. So by seeing the pattern, remember I see a pattern where I stands for inductive reasoning, you should be able to figure out the next number using inductive reasoning. And so if 22 is the last one, if I add 2 to it, I get 24. So the next number in the pattern would be 24. The next number in the series would be 24 because I see the pattern. And so 24 would be my conjecture about what number comes next in the series. And if you got it right, you just use inductive reasoning again. See, it's not that hard. You've already gotten 2 right. Okay. Now I'm going to make a conjecture, and I want to see if you can prove me wrong. So I'm going to look at the 11 numbers from the previous problem. 2, 4, 6, 8, 10, and so forth. Now when I look at these numbers, I notice that all of these numbers are even. Therefore, I can make a conjecture. And the conjecture I want to make is that all numbers are even. Here are 11 examples right there. There are 11 numbers, and they're all even. So I naturally make a conjecture that well, all numbers must be even. So, can you prove me wrong? Well, if you think about it for a second, maybe you'd want to say, well, wait a minute. How about number 3? It's a number and it isn't even. So if you're telling me that all numbers are even, I'm saying you're wrong because 3 isn't even and it's a number, so you can't say that all numbers are even. So therefore, the above conjecture is wrong. Not all numbers are even. And if you're able to do that and say, hey, wait, what about 3 or 5 or 12 or 12 and a half or negative 43.2? Those are all numbers that are not even. And if you could come up with one of those, each of those, we say that's not true, each of those is what's called a counterexample. And so you just used a counterexample. What is a counterexample? A counterexample to a conjecture is an example for which the conjecture is not true or is incorrect. So it turns out that not all conjectures are true. Conjectures are just what our guess is based on the pattern we see in inductive reasoning, and sometimes we can see the wrong pattern or just make a mistake, and so not all conjectures turn out to be true. Just like from the pattern of numbers I saw, I conjectured that all numbers were even, and of course that's not true. And you can prove a conjecture is false if you can find just one counterexample. Just like that last example, we said, hey, how about 3? If 3 exists and it's a number, then it's not fair to say that all numbers are even, because 3 isn't even, and that was a counterexample. And just like in the last example, we had 11 numbers that were even and only 1 that wasn't even, and we knew the conjecture was wrong. You can have 1,000,000 examples that show your conjecture to be true, but if you can come up with one, only one is all you need. If you can come up with one counterexample, then the conjecture is wrong. So let's do an example of counterexamples. And this first one we'll do is nothing to do with math, just the real world. And so what if I make a conjecture that says, a person of color could never become president of the United States? That's my conjecture, that a person of color can't become president of the United States. Well, let me show you some evidence of that. Here's pictures of the first 14 presidents. Not a person of color among them. So, hey, look, my series is looking pretty good so far. Next 14 presidents, again, nothing but a white face among them. A person of color could never become president. Looking better and better. My conjecture is looking more and more accurate. 14 more presidents, 14 more white faces. Again, all these things are examples of my conjecture. A person of color could never become president of the United States. But there is a counterexample, and hopefully you all would know what that is. And that example is Barack Obama. Barack Obama is a counterexample. If I look at that conjecture, I know that conjecture is not true. You can't say a person of color could never become president of the United States because one already did, and his name is Barack Obama. So that conjecture is false. And thank goodness it is. Now let's do an example for a counterexample with math. Not geometry, just regular old math. And what if I tell you that my conjecture is if I take any number and I square it, the square of any number is greater than the original number? Okay, let's start with 2. If I take 2 and I square it, I get 4. And 4 is indeed bigger than 2. So the square of 2 is bigger than 2. So check. So far my conjecture holds. Let's try it with 3. 3 squared is 9, and 9 is bigger than 3. Check. 7. 7 squared is 49. 49 is bigger than 7. Check. Same thing holds true for 12. 12 squared is bigger than 12. Check. Let's try a really big number. Let's try 100. 100 squared is 10,000. 10,000 is bigger than 100. Check. So, can I come up with a counterexample? Well, if I choose a number that is less than 1, so for example, a half, if I square it, is 1/4. And 1/4 isn't greater than a half, it's less than a half. So it is a counterexample that proves my conjecture wrong. It is not true that the square of any number is greater than the original number. That's only true for some numbers. The examples we gave, the first 5 examples we gave are true, but the last one is a counterexample proving my conjecture wrong. Now let's do an example that's actual geometry, but I promise you can do it. It's very easy. What if I tell you that any 3 points will always form a triangle? No matter what, if I take 3 points, they'll form a triangle. So let's try that. There are 3 points right there, and if I draw lines in between them, or line segments to be more accurate in between them, there's a triangle. So check, that's my conjecture holds. 3 more points, another triangle, another example that proves my conjecture. 3 more points, yet another triangle, another check. Looks more and more like 3 points always form a triangle. But there is a counterexample. And that counterexample would be, for example, those 3 points. Those 3 points don't form a triangle, they form a line. They're all on the same line. And so they do not form a triangle. Those are what are called collinear points. And so these 3 dots at the bottom, or 3 points at the bottom, are a counterexample that prove my conjecture wrong. It is not true that any 3 points will form a triangle. And there's yet another example of a counterexample.